Hello everyone and welcome back. So this time we're going to actually practice using Avogadro's number to solve a simple problem because examples are important. So let's jump into this and see how it goes. I'll move myself up here this time to get out of the way. Okay, so how do we use Avogadro's number in this equation we just found to help ourselves? Now Avogadro's number doesn't come in here directly, just know that it was used in everything that we're looking at. So we're going to check out a simple problem. So let's say that you were given 5 grams of hydrogen. Now this is molecular hydrogen, that's why it's H2. A little 2 right there is important. That says each molecule of hydrogen has 2 atoms of hydrogen. I'm asking how much molecular oxygen, that means, once again, 2 atoms of oxygen per molecule, in grams when you need to completely react, leaving only H2O. Well, first you're going to need some chemical equation, which I'll always give you. So that's 2 molecular hydrogen plus 1 oxygen is equal to 2 water molecules. Now, just to start off, this does not mean at all, no way, never, that you need 2.5 grams of O2. I've got 5 grams of H2. Well, it's 2 to 1, so 2.5 grams of O2. The only way that would be the case is if they had the same molecular weight, and they do not. Oxygen is way bigger than hydrogen. Okay, so that's step 1. Look at the equation and see the relationship. Step 2 is to look at your periodic table. Now, your entries in the periodic table are going to look something like this. You'll see a letter that's going to correspond to what you saw in the equation. Underneath that, you will see the name, and then underneath that, you'll see some number. It will never be a whole number unless you have a children's version of the periodic table. It will always be like 1.008. It'll have some sort of decimal. Now, where does that decimal come from? You're like, well, didn't you just tell me? Did you lie? You said that hydrogen has only 1 proton, and the mass of a proton, a mole of protons is 1 gram. So why is it 1.008 grams? Well, this is because this is the average molecular weight of hydrogen. And sometimes hydrogen has a neutron. It's very rare. Sometimes it has 2 neutrons, and that's extremely rare, and it's also deadly because it's radioactive. But sometimes hydrogen will have a neutron. It's called deuterium. And so it's very rare. So let's say that 99% of the time, it's going to be 1. But, about 1% of the time, it'll be 2. That'll be its molecular weight. And so if you average this together, you get, like 1.008. Now, this is not the right percentages. I'm just making it up as I go. But that's why it's not a whole number. And as you get up in the periodic table, you see that there's more and more and more examples of kind of craziness like that. Okay. So I look at the periodic table. What I see is that 1 mole is equal to 1.008 grams. However, that's of hydrogen, just 1 atom, not molecular hydrogen. So what this tells us is that we would have, roughly, is that 5 grams of hydrogen, just atomic hydrogen, would be 5 moles of just hydrogen atoms. Or since we have H2, we divide that number by 2, and we'd have 2.5 moles of molecular hydrogen. Okay, you see the connection there? Because H2 is twice as heavy, we would have half as many moles in the same amount of mass. Okay. Now that we know how many moles of H2 we have, we're going to look at the ratios. So it was 2 to 1 earlier from our equation, and that should be equal to the same thing with our number of moles we have. So 2 to 1 is equal to 2.5 to x. You could also write it something like this. 2 over, that's too low, so I'm just actually going to let me right there. I'll put it above it. So 2 over 1 is equal to 2.5 over x. Just a ratio. And so very simple algebra. If you solve that, you get that there should be 1.25 moles of molecular oxygen. Okay, so we know how many moles of oxygen, and so we're just going to be using that same equation over and over again. I didn't write it down, but this is what we're using every single time. And we're going to use that to solve for how much mass of oxygen we will need. Okay, so the molecular weight of oxygen, just atomic oxygen, is 16. However, we have molecular oxygen, that's O2, so we have to double it. So it's not 16, it's roughly 32 grams. It's slightly less, but I'm rounding here to make things simple. So it's roughly 32 grams. So we plug it in, 32 grams per mole times 1.25 moles will be 40 grams. If you have 5 grams of hydrogen, you'll need 40 grams of oxygen to completely react. So you see there's a lot less mass of hydrogen there because it's a much smaller atom. Okay, so with this we've done a single example. You can kind of see the steps you go through. It's going to be going back to the periodic table a lot. There's one online called the dynamic periodic table. It works really well. I strongly suggest you check it out. It's also really fun when you're trying to look at isotopes, which are when you have things that have different numbers of neutrons. It tells you all the probabilities, which is really cool. So hope this helped you, and I'll see all of you next time. Bye-bye.